My name is Richard Williams, and I've been teaching for Staties now for 7 or 8 years, something like that. But prior to that, I spent 38 years in the chemical industry by training. I'm a chemical engineer, and I've done quite a bit of product and process development, improvement. So one of the tools that I think has been grossly underutilized has been design of experiments. So in my prior career, I did my best to advance the use of these tools because I really believe in their effectiveness. So I'm very happy to spend an hour with you today talking about design of experiments and just kind of orient where this particular webinar is directed. This is really meant to be an introduction or a first look at the concept of designing our experiments, and we'll use Stady's Design Expert as the tool to demonstrate how to do a design experiment and what's the benefit, right? So that's kind of the main goal for today. So to prevent audio disruptions, we do have everyone on mute, except for me, hopefully. So I think that's working. You can put questions in the question area in the webinar. So if you could find that, you can go ahead and type in a question when you have one. We will spend an hour together today, and I'll make every effort to kind of work in the answers to the questions as they come up. At least the more brief questions, I should say. But after the webinar, if you do have additional questions that didn't get resolved and you're interested, please send those questions to stathelp@staties.com. And we'll make an effort to get you a more complete answer than we can do in our brief 1 hour today. Also note that the slides for this webinar and also a recording will be posted on our webpage within a few days. Okay, so that'll be out there. More on that a little bit later. So we will talk about design of experiments, and we will use Stady's software to do it. And we have two different software versions available. We have our Design Expert, which has been with us since 1986, I believe. Obviously, continuously improved and developed and extended to support more and more types of designed experiments. But we also have a flagship product called Stady's 360, which has a few more bells and whistles that would be suited for much more advanced applications. So both will certainly accommodate the kinds of things that most of us would be doing. But obviously, the Stady's 360 would be one step beyond. We also have a lot of webinars and other training available on YouTube, Statistics Made Easy. And you can look at those at any time by going to YouTube and just type in Stady's, and it'll bring up a listing of, for example, this webinar, but also some other ones that would probably be of interest if you're going to get in a little bit deeper. We also offer more advanced training, or more complete training, I should say. We have modern DOE for process optimization, which, as the title indicates, would be a little bit more focused on process type work. But we also have mixture designs or formulation type designs, which if that's your environment, if that's your world, that could also be of interest. Okay, so those are available. There is a distance learning or Zoom type version that's offered several times a year. And then if your company has multiple people interested, we can do in-person training as well. If you're interested in having some information kind of tap you on the shoulder once or twice a month, you can also sign up for staties.com publications sign up, and you'll have not a lot. We won't pester the daylights out of you, but a couple of emails a month to make you aware of DOE in training opportunities and other related ideas. So today what we're going to do is, first of all, let's just touch on what a designed experiment is. And, what's in it for me? Why would you think about doing a designed experiment as opposed to some other approach? We will get into probably the most tried and true simple designs called a two-level factorial design. These have been with us for a century or so. So the mathematical underpinnings of this predates computers, and this was just a way to get people to think about experimentation a little bit more completely and to take advantage of some statistical concepts. We will demonstrate that using a filtration rate case study. And oh, by the way, if you have access to our software, this entire case study is available to you to complete on your own and to explore. It's in the help section. I'll show you that later. So traditional experimentation, often referred to as one factor at a time, has been more or less considered the scientific method for years. But it's inefficient and it's overly simplistic, and it really is ill-suited to the kinds of things that can be studied and accomplished with a little bit more advanced approach. But when I was in school, and probably many of you as well, we were kind of taught that, well, if you're going to learn anything, you can't change more than one thing at the same time. You have to keep everything constant, just change one factor and explore the influence of that factor, right? So, okay. However, the mathematicians have revisited this idea, and they learned if we carefully design our experiment, that in fact, yeah, we won't learn anything. We stand a chance of learning everything, that there's a whole lot more that can be discovered if we actually design our experiment. We spend quality time designing our products, designing our processes that create those products. And it turns out if we put a little effort into designing our experiments, that we can become more effective and more efficient. So let's see how that plays out. So a designed experiment is a script, if you will, or a we're going to actually go out and conduct very specific runs in order to complete a mosaic of information that will help us discover. I do not see a seminar. Okay, so let me see here. Just to double check where we are people seeing my screen and hearing my voice? If I could get a reaction with the hands up, I'd appreciate it. Okay, we are. Okay, so I will try to thank you so much. I will try to come back to that question and explore what's happening there in a bit. Okay, so a designed experiment, right, is going to be a particular script or detailed plan of experiments that will have certain mathematical properties that will allow us to discover a whole lot more than we could with the same amount of experiments doing it a different way. So yeah, we have, for factorial design, we're going to do something like this cube over here, and I'll explain what a factorial design is more completely later. But we have design of experiments for mixtures. The triangle is kind of a representation of a three-component mixture, three-ingredient mixture. The cube is how it would lay out for a three-factor factorial design. So if I'm making cookies in the kitchen, it might be time and temperature in the oven. It might be the choice of cookie sheet, whether it's aluminum or Teflon or whatever. And then we have a response surface design layout in the bottom, where we can do a little bit more to optimize a system than to look at merely the contribution of the factors. So there's all kinds of different DOEs, but they do have one thing in common. It's a statistical test plan. It's a specific script. It's going to give us information about many things all at the same time, and it'll give us the maximum information with the minimum amount of runs. So if we view the world as us chemical engineers tend to view it as some sort of process, let's think about making cookies again. What we're going to do with a designed experiment is we will have a systematic series of tests or experiments in which purposeful changes are made to the input factors. So what are the input factors? These are the X's. And we might think of, again, making cookies in the kitchen. We might think of some of the things that we might want to change would be for the process of baking the cookies anyway. We might change the temperature in the oven. We might change the time in the oven. We might change the type of cookie sheet. We might change which rack in the oven we're going to use. Okay, so there's all kinds of different things. Um, and we're going to have a response, a why, right? We're going to have something that we're trying to evaluate. It might be the taste of the cookie or the yield of the cookie or both. The yield of the cookie might be cookies that aren't burned and that are properly cooked, not over or undercooked. So we might have more than one response. And our job as experimenters is going to be to relate the X's and the Y's, right? We're going to look for cause and effect. So at DOE, we're going to have a systematic series of tests in which purposeful changes are made to input factors so that we can identify the causes for significant changes in the output responses, right? We're going to change the X's in a prescribed pattern in order to evaluate the impact on Y. And what's different between a DOE and any other type is the particular series of runs that we're going to do are going to be prescribed. It's a very specific pattern of runs. It's not just a collection of happenstance data that we're going to somehow try to analyze. Now the problem in the real world is we're going to have these things called noise that are there to distract us. Okay, so for example, if I make 10 batches of cookies in the oven, and I want to evaluate the flavor, perhaps I'm going to have a panel of 5 taste testers give a rating, on a scale of 1 to 10 or something like that. Well, they might take the same batch of cookies and they might award a little bit different score each time. So if I took the average, perhaps, I would get you know, 7 the first time, 7.5 the second time, right? So there's going to be some variation based on our measurement system. We might have variation from our processes, though, as well. We might set our temperature in the oven at 350, but the oven might cycle. It might sometimes be 325, other times 375, or corners of the oven might be one temperature versus another. So the temperature that the cookie experiences might not match the set point exactly, and that might have an impact on the results. These are noise factors that could cause us to have variation in our results, and we may have trouble correlating our X's and Y's because the noise might disguise the relationship. Okay, so there's a question: the slides, will they be available? So the slides will be available as well as the recording on our website within a few days. So the vocabulary, things to be thinking about. We have our controllable factors, we'll call them X's. These are the input variables that we can change during the experiment. They could be numeric or categoric. It might be time, temperature. It might be the vendor, right? Maybe we have, for making cookies, it might be the 2 different vendors for the flour that we use, okay? Categoric choice. We have responses. They could be numeric, and they could be, they should be numeric, actually. Might be yield, tensile strength, flavor, taste, yield, lots of different things. But we also have these uncontrollable factors, the Z's. These are things that may fluctuate during the experiment, but they may also have some impact. Maybe the humidity or the ambient temperature, or our raw materials are degrading over the course of our experiments. Those kinds of things. Our z factors can go by different names, or the influence of the z factors can go by different names. And you might hear us refer to that as noise or experimental error or the residual, right? So the context will dictate which term is most appropriate, but they're all basically the same idea, this random variation that we see. So our role as experimenters is to identify the factors, x's, whose impact on the responses, y's, exceeds that would be expected given the amount of noise in the system, right? We want to separate the noise from the signal. So here's a little example that took place some time ago. A company called SKF was trying to improve their bearings. Specifically, they were trying to improve the bearing life measured in hours, and they were trying to minimize the cost of the bearing, right? So better performance, lower cost, which is, kind of a common thing that most of us have faced at one time or another. So what they did is they began with a one factor at a time experiment. Okay, right? They believe the old mantra that you can't learn anything if you change more than one thing at the same time. So what they did is they had a starting point. They had their uh, they had their standard conditions right here. And then what they did is they measured the bearing life, whatever the units were, 17 days, weeks, hours, I don't know. But there it is. So we have 17 was their standard operating conditions. What they did then is they changed factor A and they went from 17 to 25. Well, it was an improvement. May not necessarily have been deemed spectacular, but yeah, that was improvement. So then what they did is they went to factor B and they made a change and they had basically, the same kind of influence with factor B. It went from 17 to 26. Then factor C was a raw material change. So they went back and changed one factor at a time. They just swapped out the raw material and they had a minuscule improvement in the performance as well. Okay, so the conclusion that they were reaching was the factors being evaluated really won't materially change the bearing life, right? They're looking for, an improvement by a factor of 5 or 10 or something like that. And yeah, they could have some modest improvements, but it wasn't going to take them where they needed to be. So then the new engineer comes in and says, right, the new hire comes in and says, I heard something about design of experiments. And they said, yeah, that won't work for us. We don't believe in it. We have too much noise in our system, what have you. They just didn't think that it would be particularly helpful. But he talked them into it. And so what they did is they came back in and they ran a designed experiment. So what would the designed experiment look like? Well, with a three-factor two-level factorial design to look at the impact of the factors, they would complete the cube instead of just doing half that was done here. They would complete the cube. They would do these other uh, you know these other four conditions that weren't previously run, and that would specifically allow them to evaluate the main effects, yes, but also something called interactions that we're going to learn a whole lot more about in a moment. It turns out that if they had not done a designed experiment, they would have missed the whole show. It turns out that there's an interaction between these three factors that would allow them to see the synergistic effect to take them all the way to 128. And the way this thing translated in the end, once they actually put it into practice, they actually saw a full tenfold improvement from their standard conditions to the optimal conditions. So they quickly became believers in the idea of design of experiments. And I'll get the right tool here. Let's see. So the traditional approach to experimentation, the one factor at a time while holding all other factors constant, is a very simple, it's very understandable. I can see why all of us would be tempted to believe in such a concept, but it's also inefficient. It's serial processing, right? First, we'll test go from the standard to this one, then the standard to that one, then the standard to that one. So it's inefficient. It's also, compare that to a factorial study. We're going to have multiple factors changing at the same time, but in a very specific pattern, in a very specific way. In a factorial design, we're going to change each factor between a high and a low level, and we'll look at all the combinations that are possible, right? So low, low, high, 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 low, etc. If we have 5 or more factors, however, we can generally take shortcuts. So we're not going to run all the combinations. So we begin to abbreviate the work, right? So there are some advantages once we hit 5 or more factors. And the beauty of it is we can account for interactions between the variables. And breakthrough performance is often hidden behind or requires us to evaluate this thing called interactions. And we're going to maximize the information with a minimum amount of runs. So there are multiple types of design of experiments. We mentioned factorial, and again, those are designs that have been around for perhaps a century or so. Very effective. I would say that to date, probably factorial designs have been the most utilized type of DOE. If you have any familiarity with DOE at all, it might be factorial designs that you're familiar with, or if your managers or instructors have brought focus to use a DOE, it may very well have been a factorial design that was being thought about. However, the mathematicians have been busy in the past century, and there are all kinds of different designs that are now available for different purposes. We have response surface designs, which, as you'll see a little bit later, you can start with a factorial and broaden it out to a response surface design to kind of bring out the magnifying glass and really hone in on where the optimal conditions reside. We have special designs for mixtures. That are a little bit, they're like response surface designs, but they're tailor fit for formulation work. For all 3 of these, if you have a continuing interest, I would suggest that maybe you take a look at my webinar called New User Intro to Design Expert Software, where I actually in 1 hour do an example for each one of these 3 different DOE types, so you can get an idea of what they're for, when to use them, and a little bit more insight on how to use the software to get it done. That webinar is a very concentrated 1 hour, but I'm partial to it. So, factorial design, we learn about the main effects or the factor influences, and we also learn about interactions. An interaction is when the impact of one factor depends on the set point of another factor, okay? And we'll see that play out in our example. Factorial designs are very useful for screening. Perhaps I have, 10 or 20 different factors that I imagine could impact the flavor of my cookie, and I want to do the smallest amount of work possible to decide which of those factors actually has a meaningful impact. Well, a screening design can take us there. We can also do a characterization study where we will do just the right amount of experiments to learn about 2-factor interactions as well as the main effects. We can do a response surface now where we're going to actually mathematically build something a little bit more complicated, like a quadratic model to actually fit to our data, so that we can shop for the optimal conditions, right? So this picture on the right is a look at what a factorial design augmented to become a surface response, what that would look like. So we would take the cube again that we saw in the factorial, but now we would add some center points, and we would add these axial points in order to fit more complicated terms than can be fit with just the 2-factor high-low evaluation, or the 2-level high-level evaluation. And mixtures, so a mixture design or formulation is where the responses are what really matters is the proportion of the ingredients. Okay, so when I make cookies, it's not the absolute quantity of sugar that I put in that matters. It's the ratio between the sugar and the flour, or what have you, or the butter and the flour. It's the ratio of ingredients. And a mixture design is similar to a response surface, but it's tailor fit for the formulation world. It has to overcome some various constraints, and it's going to use a different type of polynomial that's used, not the standard Taylor series that's used in response surface. We're going to use something called Cepheid polynomial. So at the end of the day, mathematically, they're built specific for formulations, and they're a little bit different than standard response surface, and the difference matters. You can take a look at a recorded webinar called Crash Course for Mixture DOEs if you work in the formulation world and want to understand a bit more about that. So a two-level factorial design. So let's get into what that would be and how it works. So the mathematics is, again, this was first put together 100 years ago, well before computers, and so it was meant to be something that good results could be achieved with quite simplistic, calculations. And this is how it works. In order to to conduct uh, a factorial design, what we're going to do is look at all the various combinations. So here we have factor A and we have factor B. So it's a two-factor, two-level factorial design. When we run them, let's say this is temperature, I'm making cookies again. So that's the temperature in the oven, and this over here would be time. What we're going to do is we're going to pick a high and low value to evaluate. And we're going to code that -1 and +1, right? So whatever temperature we pick to be the low value is coded as -1, and whatever temperature we pick as the high temperature will be coded as +1. And the same thing over here for the time, +1 and -1. Then what we will do is we will evaluate for factor A. Let's take a look at what happens when you have temperature at the high end. Well, we have two cases where we evaluate the temperature at the +1 level. So what we'll do is we'll take the average. We're going to look for the effect of factor A. We'll take the average, so we'll sum up these two values and divide by 2. And we'll come up with a value. And then what we'll do is we'll subtract the average of when it's low. Okay, it's very simple. It's very effective. We still have to think of what might be puzzling you is you're thinking, well, yeah, that's all true, but time is changing at the same time on us. Well, yes, it is. But what we're calculating here is going to be the main effects. Okay, when we do that. And I'll show you in a second how we do the interactions. And how do we calculate, B then? Well, we would take the average of when B is high, and we would subtract the average of when B is low, and that would be the main effect for the impact of time on our design. Okay. Now if I get the right tool here to erase all ink. Okay. Now how do we do an interaction? Well, an interaction, and I'll show you on the next slide how the math works out, but an interaction would be when we compare the diagonals. Let's take a look at the average of those two, and we'll subtract the average of these two. And in the same way, then we will calculate in this case, it's the two-factor interaction effect, right? We'll compare the diagonals. If the diagonals are equal, then there is no interaction term. Okay, if the diagonals are not equal, well, then there's something going on that we'll call an interaction. So that's kind of the key point there. And get the right tool back. All right. So with this three-factor two-level design, we have 8 data points. So we're collecting 8 unique designs, eight unique data points, right? Each one of them has a distinct combination of the 3 factors. Those factor combinations are described by the three-letter pattern here, right? So the first run is minus, minus, minus. Well, that's in the bottom left-hand corner where everything's set at its low value. And then, number 8 is plus, plus, plus. So everything is set up here at its highest level. And then you have all the various combinations described by the three-letter plus minus patterns, and that's where you get the unique runs here. Okay. We also have two-factor interactions, AB, BAC, and BC, that we can evaluate, and then also something called a three-factor interaction, right? And they all have their unique plus-minus pattern as well, okay? So what we can calculate with 8 runs is we can calculate the overall average. That's 1 degree of freedom in statistical speak is used to calculate the overall average of the data. And then we can calculate 7 different effects as well. Because I have 8 runs, I can calculate 8 different things. So I got the overall average and 3 main effects, 3 two-factor interactions, and this thing called a three-factor interaction. Hint, hint, three-factor interactions are very rare, and oftentimes we'll assume they don't exist. But that's coming up later. Okay, so that's how it's laid out. So it's a very specific order that we're going to run these things, or at least, let me rephrase that. There is a very specific thing called standard order, but we don't want to run our experiments in standard order. We want to shuffle the deck. We want to randomize these runs. Well, why would we do that? Let's imagine we had something drifting through the course of our experimental path. Let's say we're making cookies in the kitchen, and let's say that humidity actually mattered, and the humidity in our kitchen is drifting throughout our 8 runs. Okay, so early in the day, maybe it's low humidity. Later in the day, it's high humidity. So if I run them in standard order and I look at the average of when things are positive and the average of when things are negative, the risk I run is I would confuse that lurking variable, the rising humidity, I would confuse that with the impact from factor C. Okay, now that might be a little bit more of an advanced concept, but the takeaway message is we don't want to run our experiments in something called standard order. We want to randomize that so the effect of the ambient humidity or whatever our lurking variable is not confused with one of the factors we're trying to study. So the advantage, it's a simple structure. It requires minimal runs. And if we have 5 or more factors, we can begin to abbreviate the pattern. We have something called hidden replication because for each factor, we're getting multiple looks at what takes place when a factor is at the high setting versus the low setting. Okay, yes, we have other things changing, but we have more reads on that, and if we untangle the mathematics of it, we can really understand how much impact is coming from the interactions, how much experimental noise we have, etc. You'll see that develop as we continue. We're going to look at more combinations of our factors than one factor at a time. That gives us a wider inductive base, right? We complete the cube. We don't just look at half of it. And we're going to see interactions, and that's key to new discoveries. It's easy to analyze. The math is simple. We're going to use graphs to even make it easier. And if we want to advance this to a response surface design, if we feel we need to find the optimal conditions on the interior of the cube, this can serve as the basis for a response surface design. We don't throw away data, we add to it, we augment it. So in our software, when we open it up, and we will in a moment, it's going to open to this particular screen. It's going to default to setting you up for a 2-level factorial design. And you'll see when I open the software that, this is one of many choices one could make, but this is the default entry screen. This chart shows, various colors, and they have the implications that you would imagine. Let's start with the white designs. These are the full factorials, where everything is tested in combination with everything else at both the high and the low level. So all combinations, all corners of the cube, if you will, are evaluated. But we also have green designs. Okay, well, the green designs will require less work, less runs, and they will be completely suitable to identify the main effects and two-factor interactions. They won't identify, or they'll at least, it'll be, we'll have something called aliasing take place. You won't get a clean read on three-factor interactions with the green ones. Well, yeah. So that's a little bit what's happening here. They're often a good choice because we're primarily interested in main effects and two-factor interactions. The yellow ones, are going to use those with caution, but where these are useful is for screening, right? Remember that example where we have 20 different ideas of what could improve the flavor of a cookie, and we want to cut to the chase with as little work as possible. So what we're going to do is perhaps use one of these yellow designs to really abbreviate the amount of work, and they will let us know what main effects are making a contribution. We'll be a little confused about two-factor interactions, and we may need to take a subset, the factors that survive the screening. We might want to do a full factorial to more completely understand the interactions, but at least we'll be working with the only the factors that survive the screening. And the red ones, well, that's kind of what you would imagine is, apart from some very specific purposes for robustness testing, we fundamentally won't be using a red design because if two-factor interactions exist in the system, you are guaranteed to get the wrong message. Main effects are confused with two-factor interactions. So if it's factor A that it says matters, well, it might actually be a combination of B and C, and you won't be able to know if factor A mattered or not, right? So we're going to avoid using the red designs. All right, well, let's do a little less talking and a little more doing. So let's begin setting up a little case study that we have. So here we have a filtration rate. And the reason we're going to choose this particular one to demo is if you have access to our software, you too can look at the help screen tutorials, two-level factorial filtration rate, and you could actually go in and see the script for this exercise and also have the data set. So, and there's lots of other tutorials on there as well, but this is one that's in the system. So Doug Montgomery and his grad students were, Doug is the guru, or one of the early gurus of design of experimentation. So he and his grad students were asked to help explore a situation where we have wafer board that's going into mobile homes that has an odor problem. Worse than that, it's a health problem involving a chemical called formaldehyde, which is a bad actor. It's not a good thing for us to be breathing. And the reason that it was being used in the manufacture of wafer board is it tends to thin the glue involved to glue these wafer boards together, and it would improve the filtration rate of the glue. So what they want to do is at least cut the formaldehyde content in half. It's currently at 4%. They'd like to get it down closer to 2% if they can. But the goal is to explore other factors that might allow them to sustain the good filtration rate so they can be productive at the same time. Okay, so find the process conditions that reduce the concentration of formaldehyde while maintaining a high filtration rate. So what we'll do is we'll go in the software and we'll set this up. We have, these are the processes that, or excuse me, the factors that we're going to evaluate. These are the ranges that the engineers decided to take a look at. Okay, and who gets to pick that? Well, you do in your world. So we want to set realistic ranges for each of the factors that we think might make a difference. And then it's going to do this thing called a power calculation, which is a little bit beyond the scope of what we're going to have time to talk about today. We do have a webinar on that. I'll leave you to discover that. But the whole point and purpose of the power calculation is to help us properly size the experiment. So what do we mean by that? Well, we need to be able to find what we're looking for. In this case, we're looking for factors that would impact 10 gallons per hour, the filtration rate. And we have a standard deviation, right? Remember, our job is to find the impact of factors despite the presence of noise. So if you have a lot of noise, you're going to need a lot more runs in order to detect the signals apart from the noise. Okay, so that's about as deep as I'm going to go on that, other than to say here we have a power of 95%, which is good. We usually want to be at least 80. And what that says is, given the amount of noise, the standard deviation in the system of 5, we can detect a signal of 10 with 95% confidence. That's pretty solid. So let's go on the software. So let's see if we can get this to open up for us. Okay, so here's the software. Here's what we saw. We have 4 factors that we're going to look at, which is going to result in 16 runs. I can't shortcut it because I would go to a yellow one and I would not understand the 2-factor interactions very well. So we'll do the 16 runs. I will click next. Oh, on the left-hand side, you can see that there are many, many different types of designs that could be chosen, right? So we're going to show you the factorial, but even in factorial designs, there are a number of designs that would help us accomplish our goals with less work, perhaps, address situations that the standard designs wouldn't necessarily handle. We have response surface designs, we have mixture designs. So there's a whole menu of opportunity here to more fully explore, but we'll begin at the beginning of the DOE journey and do a factorial. So here we are. I have 4 factors. I will click next. I have them entered here, right? Everything that was in the slide handout, and that you can find if you come into help, tutorials. What's this one? I say this is 2-level factorial filtration rate. You could click on that and get the script for this exercise. And you could go to tutorial data, come down to filtration rate and get the data set for this. But anyway, so you could follow along. Here I have that power calculation. So I want to make sure that I put the numbers that were given to us, the 10 and the 5, and the ratio is 2, right? 10 divided by 5. And that drives that power calculation. And the blue boxes, the annotation boxes, help us understand the key information on each of the screens that we're looking at. It's a stat ease, so we want to make it easy for practitioners like you and me to come back in and make sense of what we're seeing. So here it says power should be at least 80% or greater, and yep, we're good. So there it is. So we'll finish the design, and we have our 16 runs. Notice that I have the standard run order and I have the randomized run order, right? Which one can re-randomize if one chooses, but there it is. So that we don't run it in standard order. We want to make sure that we protect it against the potential impact of those lurking variables. Well, then we get our data. And to get my data, I'm going to go to Help, Tutorial Data. I will look at filtration rate. And it calls this up. And if I go back to the upper left-hand corner, the design, I see the same table of information now completed with the data. So we've gone out there and we've measured the filtration rate for each one of these unique sets, combinations of factors. Once we have our data, we analyze it. So we're going to come down here. The typical menu path is more or less top to bottom here. So under Analyze, we will click Filtration Rate, and we'll begin by clicking Start Analysis. Okay, so that brings up a couple of graphs. So what our task is at this point in the journey is we want to figure out which factors belong in the model. So the model now is going to be a predictive equation that we're going to use, well, to what? To make predictions for our yield. And not every factor in the system is going to necessarily have an impact. So what we're going to do is we're going to use this half normal plot to separate the noise from the signal. The red line represents noise in the system, and anything that falls along that would be a factor or interaction term that is inconsequential. So let's just pick one of those. Let me right click on it, pressure. So there's the second one. Pressure falls right on the red line or along the red line. So that has been determined not to have a material impact on the filtration rate, which is interesting. And I'll more on that a little later. But what I'm going to do is I'm going to draw a box around all of these other factors. These are statistically significant because they pop off the red line. So I have temperature, I have stir rate, and I have concentration. But look, I have two really important two-factor interactions. There's an interaction between temperature and concentration, and another one between temperature and stir rate. Okay. One factor at a time experimentation would not have identified those two very important interactions. We could take another peek over here at the Pareto chart to look at the impact, or another view, if you will, of choosing factors. And, maybe we could, put the three-factor interaction. I could click that. That didn't seem to be, that's close to the red line. But sometimes we're not entirely sure if we should select something or not select it. The final judge is going to be the next screen, which is going to be the ANOVA, right? So we select different things. Let's see. Let's say I selected pressure, okay, even though I don't think it's important. Well, then I would come to the ANOVA table. And to make a long story short, I'm creating a predictive model which is comprised of these particular contributors, right? These are the factors that are statistically significant. But I'm going to look at the p-value. The p-value is eventually the criteria that we use to determine if one of those factors or interaction terms was in fact, legitimate. And in the blue box, it says that we're looking for less than 0.05. 0.05 would be 95% confident that something mattered. Well, here we have pressure, which is way above the 0.05. So in fact, we made the wrong decision. So we would come back and we would turn pressure off. Okay, that wasn't having a statistical. So p-values are our friend here. We want a statistically significant model. And what is the model? Well, if I look at the so going back to the effects, if I look at the numeric version of this thing, I'm building up an equation from the model terms. So temperature, concentration, stir rate, these two-factor interactions, they're all used to build up the model. Everything else that falls along the red line is being used. They're not included in the model, and they will be used to evaluate error, which is why it has the little green E. That's going to be an estimate of experimental error. So we have R-squared type information here. The R-squareds between there's a nuance between R-squared and adjusted R-squared but basically what we're trying to discern with those two is what portion of the variation in our data set is explained by the model that we use, right? The predictors that we use, how good of a fit can they create? And we're basically at around 95%. Our model is pretty good. It can make predictions or it fits with about 95% accuracy. The predicted R-squared is an assessment for how good would we anticipate this model, predicting the next case. If we went out and ran a different set of conditions, how good would we be making those predictions? And, that's also pretty solid. But what we're doing is we're using this now to create this equation. We calculate these coefficients in the prediction model, and that's used to create a coded equation. Remember, each factor is coded to be -1 and +1. So here's the coded equation. And we also have an actual equation. So the temperature, concentration, so it's a little bit more of a good model to use in order to make predictions if you had the actual temperature, etc. Okay, so we've created the model. Next thing we want to do is see if we have any outliers or oddities taking place. So we're going to look at the diagnostic plot to make sure that our system makes some sense. Here, our residual, what's a residual? Our residual is the difference between the predicted and actual for each one of our data points. And over here in the report view, we actually calculate the actual value, the predicted value, we calculate the residual, the difference between the two, okay? So what we do is we plot those residuals to make sure that they are normally distributed. And if they more or less fall, more or less on that red line, then we consider them to be normally distributed. What we don't want to see here is a great big S shape pattern or something like that. So modest deviations are fine. The software is robust enough to handle modest deviations. But if you have a big sweeping S shape, we're going to have to do something to deal with that. We're also going to look at the residual versus predicted. Here, we're going to satisfy the underlying ANOVA assumption that the residuals has constant variance throughout the range that we're evaluating. And so we're looking at the vertical spread of the data and to see if there's any patterns or anything that's outside the red lines, which might be considered an outlier that we should explore more completely. What we don't want to see here is a big megaphone shape. And here this looks like more or less, pretty good randomized data, so we're happy. We could also look at the residual versus run. This is where maybe if we had a lurking variable where, maybe I had low humidity early on, so everything was low, and then later on I had high humidity, everything was high. So we could look for patterns that were developing or, constantly increasing or constantly decreasing. Those would be indications that something funny was taking place, through the sequence of runs. The bottom left is something called the Box-Cox, and let me make that one a little bigger. This one is helpful. There's a lot going on here, but the takeaway message is over in this box in the upper left. It says recommended transform, no transform. Okay, well that's good. We're not going to use a transform in this case. Well, what is a transform? Well, sometimes analyzing our raw data is not the right approach. There are times when we want to do a mathematical operation before we look at our data. Some things are log linear, for example. So we might want to take the log of all of our data before we analyze it, transform the data before we do the analysis. Here we're in good shape, so I won't belabor that point anymore. Once we have done that, we will look at the model graphs, and that's where the story begins, or it gets good. So here it's going to plot an interaction plot. Remember now we had two interactions, an AC and an AD. So what's happening here? Well, if I asked you, well, what's the impact of temperature, or excuse me, what's the filtration rate at temperature 24? Okay. Well, the answer is, well, it depends. Okay. If the answer depends, that's a clear indication that we have an interaction taking place. The filtration rate at a temperature of 24 depends on what? The second factor, the two lines here, is the concentration. The blue is 2% and the red is 4%. So the filtration rate at 24 degrees depends on our choice of how much formaldehyde is in the system. That's an indication. These lines aren't parallel. At the high temperature, though, look at this. We have a situation where the low concentration, the 2%, is giving a pretty good filtration rate. So there's hope in this now, in this case study, because it turns out that maybe we can get a high filtration rate with a low concentration, the black line. Okay, so that's encouraging. So let's remember that we like the 2% concentration. And let's take a look at this other interaction plot, the AD. Now let's remember that we like the lower concentration. So, look what's happening. As I slide concentration down now, look what's happening. I'm liking the high temperature, 35 is beneficial. The stir rate at 30, the red line, is high. We like that. And what's really weird about that is that if I reduce the concentration, I'm actually getting a higher filtration rate. Okay. We wanted to reduce the concentration, so that's nothing but good news. And it's something we would not have found had we not understood the interactions taking place. Okay, and that's the critical takeaway here, is the breakthrough through performance is coming to us because we identified the two-factor interactions that are involving temperature. If I click on that, I can do what's called a pairwise comparison, but the key here is I can take a look at the filtration rate, and I get an estimate for what the filtration rate would become, 100.625. I can also use numeric optimization to seek out the ideal conditions. In here, I would put some criteria. What do I want to do with that? I want to maximize it. Okay. And I want to go from, I don't know, 43 is too low. Let's say I want to get to at least 60 or something. I don't know, pick a number. And then I would hit solutions, look at the ramp view, and it would give me the ideal operating conditions, right? My temperature is 35. My pressure, which was shown to be not a statistical contributor, is kind of set in the midpoint. I'll talk about that in a minute. The concentration, we like the 2%. Stir rate was at the high end, and now I can see that 100.625, the same value that I got on the graph, that's my predictor of what it would achieve on average for that set of conditions. Now, why is pressure set in the middle? Well, pressure, why didn't that matter? If you know anything about filtration, pressure is kind of one of the key factors in it, in improving filtration. So why didn't we see it? It's because we change pressure over a very narrow range. And all we can really say is pressure, when it changed from 10 to 15 psi, didn't appear to have a material impact or a statistically significant impact. Okay, so that we need to be careful not to claim that pressure doesn't matter. All we can say is that pressure didn't reveal a statistically meaningful impact over the range that we tested it, 10 to 15. All right, well, let's go back to our slides and let's make a few final points here. So we went through all of that, see if there's anything more we need to talk about. We saw all the graphs, made sure that we don't have any outliers or statistical anomalies. That gives us permission to look at the different plots. I should probably show you some of the other plots that are available. You know, we could look in these other plots here. We could look at a contour plot, right? And we could change the concentration. A lot of times we might want to look at a 3D plot. I like that a lot. So maybe we want to have two of these plots, one at low concentration, one at high concentration. Well, I can click the positive here. I'm going to do another 3D plot, and this time I'll put the concentration at the high end. So now you can compare the two different situations, and you can see where we end up with the optimal. We like the low concentration, etc. So that's one thing that could be done. So had we done a one factor at a time, the argument would be that we might not have even seen that temperature mattered. How can that be? Well, let's just take one quick peek at the software again, and let's go back to, let's see, close that one. Let's go back to the interaction plot that we saw, the AC. Oops, not that. Just clicked the wrong thing. We want the A, and I just crashed it. Okay, well, that didn't help at all. Skip that thought for a moment. That was my fault. Anyway, at the end of the day, what we would have seen is that red line, the first red line on the graph, it was not statistically different from the low temperature to the high different. So if we had done one factor at a time, we would have excluded temperature as a statistically significant factor. And therefore, we wouldn't have studied it anymore, and we would not have discovered that there were two critical interactions involving temperature because we dismissed it as a contributor. So we were successful. So wrapping this up then, we really want to get away from one factor at a time, and we want to start capitalizing on the effective and efficient DOE. That's really the way to go. We have factorial designs for looking at detecting effects. We have responsive surface for optimization. We also have mixtures. Our software is really focused on specifically design of experiments. That's our bag of tricks. That's what we really focus on. And there are webinars available. I also mentioned to you that you might want to take a peek at the New User Intro to Design Expert Software, where I go through 3 specific case studies in an hour: a responsive surface, a factorial, and a mixture design. You can take a look at Know the Score. That's another good entry-level recommended tutorial that you might want to take a look at, or webinar, I should say. You can go to YouTube and just type States and find all kinds of different things. So we invite you to do that. But that brings us to the end of our journey today. So I thank you for your attention. If you have questions, please feel free to send them to stathelp@states.com. If you are interested in exploring a license for the software, please contact sales@states. A reminder, we also have good deals for academic use, so that would be another option as well. So with that, that wraps up the webinar. Again, this will be posted on our website soon. So I thank you for your attention and wish you the best of success in your experimental journey. Thank you.